Steganography is a method used to hide messages in plain sight, whether within images, audio files, or videos. While it used to mean wax tablets or invisible ink, steganography today is done through computing methods primarily.
This picture is the image we will be hiding things in during this process, which is a form of Bergman's method, a simpler form of steganography that implements principles from linearity. During this process, we will use SVD to encode a hidden image in the less significant values of the hiding images matrix, and we will also use SVD as the means to retrieve the values from the hidden image.
This is a matrix we will be hiding within the other one. It has to be smaller in order to fit within the least significant values of the earlier matrix. This is the outcome. It's not perfect because we're using a simpler form of Bergman's method, the one he described more directly in his paper. It is not without error, clearly. Further steps can be taken later to lessen this noise. The encoding process.
What you see here is the matrix we will be hiding our image in. It is a high-rank matrix based off of the magic 8 squares you got in high school.
Here's the hidden matrix. It's 15 bits and it's in binary. Those are the important things.
The first step is to convert all of your zeros to negative ones.
The next step is to convert this matrix to a triangle. This seems super arbitrary, but you're going to use it later.
Bergman's method is not error-free. To make errors easier for the decoder to catch, multiply columns starting with negative values by -1.
To make sure multiplication stays the same throughout the process, do the same to the V-transpose matrix.
We need a place to encode the hidden image. In Bergman's method, this is a 15-bit triangle, 2 columns in and 1 row down.
To encode the hidden matrices values, take the absolute value of the stuff in the triangle and multiply it by the values that you find in the hidden triangle. To properly decode the hidden image through SVD, you have to orthogonalize this U matrix. The top row and left 2 columns are the hiding image's most significant values, so we have to rewrite the columns below, the least significant values, to orthogonalize. We use A, B, C, and D matrices to perform the operation -C transpose times A transpose times B to find D. The dimensions of these matrices will change because D does, but B will always be directly on top of D, and C will always be directly left. A will be in the remaining space.
We are going to normalize this matrix. Normalizing ensures that we can decode using SVD. To help reduce the errors in Bergman's method caused by the eigenvectors and values mixing up because the eigenvalues are too similar, we will make the least significant eigenvalues equidistant by dividing their range by the number of spaces between values.
Use the number you get to make sure that the values increment up from the least value to the greatest. Then multiply everything through in the SVD equation to get the combined image or matrix.
Now for the decoding process.
Take the values of the combined matrix you have and do the SVD to extract the U from that.
Here is the U from the SVD of the combined matrix.
Remember how earlier we multiplied things by -1 to make things positive? Well, now we're doing that again, because we remember that the entire top row is supposed to be positive, so if there are negative things, then we have to multiply those by -1 to correct those columns. Using this technique, we can eliminate any errors in the Bergman's method process.
Next, we will block off the U matrix as we did earlier to get the 15-bit triangle. We will look at the signs of the values in this triangle to extract the hidden values.
But as you recall, we didn't start with a triangle, so first we're going to convert this back into our rectangle matrix. Then we're going to undo one of our earlier steps and convert the -1s back into zeros so that we have our hidden images values.